Jack Jackson, and we're back with another video about limits and continuity. And this one is going to focus more on continuous functions and some of their properties. And so many of our most common basic functions are actually continuous functions. Some other standard functions are continuous everywhere they're defined, but they have some places where they're undefined, and those are discontinuities there. Of course, obviously, if it's undefined, it's a discontinuity. These functions that have these properties are pretty well behaved, and they have some nice properties. So we're going to continue to study continuity, but let's recall the definition of continuity to begin with. So we say a real valued function f is continuous at a point, so continuity at a point at x equals c, if and only if the limit as x approaches c of f of x is f of c. Now recall that this requires actually three things. The function must be defined at x equals c, so f of c must exist. Number two, the limit of the function as x approaches c must exist. And number three, those two values must be the same thing. And of course, a function can fail to be continuous if any part of this definition fails. For example, we've seen examples where the function didn't exist, but the limit does exist, a hole in the graph. Or we saw examples where the limit didn't exist in many cases, different ways that might happen, an asymptote or some other way of jump discontinuity. Or we could have the limit exist and the function exist, but they're not equal to each other. So there's a hole in the graph with an isolated point. So there's several things that could go wrong there. But if all this stuff happens, we have a continuous function. And most of the functions we're used to dealing with in pre-calculus are at least continuous everywhere they're defined. So this definition of continuity involves a limit. So if we apply our delta-epsilon definition of a limit and replace the limit value L with the value f of c, then we have another way to write out the definition of continuity. So for real number c and a function f defined at x equals c, then f is continuous at x equals c, if and only if, for every real number epsilon greater than 0, there exists a corresponding real number delta greater than 0, such that if x is between c minus delta and c plus delta, c minus delta is less than x, which is in turn less than c plus delta, but x is not c, then f of c minus epsilon is less than f of x, which is in turn less than f of c plus epsilon. By now you should recognize this as this is where we normally put the L right here, and of course L is replaced by f of c. And so we would use this sort of version of it to work with definitions and to prove some things are continuous or so forth. Now we have several theorems relating to continuous functions, and these theorems, one of the things that they do is they allow us to build up continuous functions from other continuous functions. So if functions f and g are continuous at a particular point c, then each of the following functions is also continuous at c. F plus g, f minus g, k times f for any real number constant k, f times g, and f divided g, provided that we don't divide by 0. So f of c cannot be 0. Okay, so this gives us a way of building up some continuous. If we have two continuous functions, then when we combine them in these ways, we get another continuous function, or at least continuous at that particular point. If a function f is continuous at some point b, and the limit as x approaches c of another function g equals the b, then the limit of f as x approaches c of f of g of x, that composition, is f of the limit of g, which is f of b. So this limit sign can be brought inside the function f if that outer function f is a continuous function. We can do that. Continuing on that, if a function g is continuous at a point c, and a function f is continuous at g of c, then the function f composed g is continuous at c. That's sort of an extension of what we just did in number 2. And number 4, the composition of two functions which are continuous where they're defined is also continuous where it is defined. And so that is, that's number 4 is just basically the same thing as 3, but just saying if this C is at any point where they're defined, then that's going to go and that's going to apply here. Now, the next one is a little bit different kind of function of a theorem. The intermediate value theorem is very important in the theory of calculus, and it says if a function f is continuous on a closed interval from a to b, where the endpoints are not the same for the y values, f of a is not equal to f of b, and let n be any number between f of a and f of b, then there exists a number c in the interval a to b such that f of c equals n. And I'll illustrate this one visually for you in just a minute. It'll make more sense out of this. And number 6 says if a function f is a one-to-one and continuous on an interval a to b, then f must be either strictly increasing or decreasing on that interval, either strictly increasing or strictly decreasing, and its inverse function, f inverse, which it'll have because it's one-to-one, it'll have an inverse which is a function. That inverse is also continuous on the image interval f of a to f of b, which is the image interval if f is increasing, and if f is a decreasing function, then this interval works backwards. It's f of b comma f of a. And so it's continuous on its appropriate interval there. Okay, so let's investigate these just a little bit more. So the proofs, all of the proofs of part 1, each of the subparts there, they follow directly from applying the corresponding laws of limits that we looked at earlier in the definition of continuity. So there's really not much to the proofs once you put those two pieces together. That's pretty much all there is. So notice we are given that functions f and g are continuous at c. We want to see that the limit of f plus g of x is f plus g of c as x approaches c here. Well, f plus g, the limit is as x approaches c of the function f plus g applied at x is the limit as x approaches c of, well, the f plus g of x is defined to be f of x plus g of x. Evaluate each of those separately and then add the outputs. Well, according to our law of limits, provided it is the limit of the first plus the limit of the second, provided these limits exist, and if it's continuous, these limits do exist, right? And not only do these limits exist, we know what they are. This first limit is f of c, and the second limit is g of c, since they're continuous. And of course, f of c plus g of c is f plus g of c. And so we see that this sum function is continuous. And this difference one works really pretty much the same way. This one works almost the same way here, except now we're applying the constant multiple rule for our limits. The limit of some constant times f of x is the constant times the limit, and that limit is f of c, and so we get what we want there, so that function is continuous. Similarly, the product function f times g of x is f of x times g of x. When we take that limit, the limit of the product is the product of the limits, provided those two limits exist. So this limit here of this product is this limit of the product is the product of the two limits, which are just f of c and g of c, and so that is f times g of c. And the same thing works here for the quotient. The quotient function f over g of x is f of x over g of x. We take that limit as x goes to c. It's the limit of the numerator divided by the limit of the denominator, which is just f of c over g of c. And this all works out just fine as long as the denominator is not 0, so we have to throw that in the hypothesis to make sure that we're not dividing by 0 anywhere here. And so those proofs are very, very straightforward, and they follow directly, really, from our properties of limits. Now, the proof is pretty straightforward here for 2. Let's remember what we're trying to prove. We're trying to prove if a function f is continuous at a point b, and the limit is g of x as x approaches c is b, then we can basically pull this limit sign in front of the outer function when we're doing a composition. So let's take a look at that. So we're given that a function f is continuous at point b, and the limit is x approaches c of g of x equals b. That's our hypothesis. That's what we're guaranteed or assuming for this particular theorem. Okay, and so For any epsilon greater than 0, we want to start with an epsilon greater than 0, find the appropriate delta so that our final thing is within epsilon of what the limit should be. Okay, so let's see if we can do something with that. For any epsilon greater than 0, since f of x is continuous, then the limit as y approaches b of f of y equals b. So we're going to think of y as the input for f, but y is also going to be the output for g. So y and g of x are going to be the same thing. This is what we get when we do a composition. The output of one step becomes the input for the next one. So there exists a number delta 1, okay, which is a positive number, such that if y is between b minus delta 1 and b plus delta 1, then f of y is between f of b minus epsilon and f of b plus epsilon. Remember, f of b is your L because is your limit because the f is continuous. So this is our continuity, our limit definition with deltas and epsilons mixed in with the definition of continuity. This is what we get here. All right, now we're also given the limit as x approaches c of g of x is b. Now let's let epsilon 1 be delta 1. So remember, we're doing like the output for one goes with the input for the other one. So the delta that we used up here is going to be our epsilon that we're going to be using for the limit here. Well, for that positive number, that particular epsilon, which was our delta up here, then there exists a corresponding delta. That's the delta we're going to need overall. Such that if x is between c minus delta and c plus delta, then the g of x is where? Between its limit, b minus epsilon 1, to b plus epsilon 1. But wait a minute, epsilon 1 is just delta 1. So that says g of x is between b minus delta 1 to b plus delta 1. So if we have x's such that x's are in here, then we have g's, which are our y's. Okay, our g or y is between b minus delta 1 and b plus delta 1. Well, we saw when we had y's there, then the final thing is that f of y is between here. So f of y is between f of b minus epsilon and f of b plus epsilon. But wait a minute, y is just g of x. So f of y is f of g of x. So what do we have? We have f of g of x between f of b minus epsilon and f of b plus epsilon. So that tells you that the limit is f of b. And of course f of b is f of the limit of g. So we can bring the limit sign inside this limit operator inside the outer function when that outer function is a continuous function. Okay, let's keep going. 3, we're going to say a function g is continuous at c and a function f is continuous at g of c, then their composition is continuous at c. So we're really just going to apply the last result. So the proof is rather short here. If a function g is continuous at c and a function f is continuous at g of c, then since g is continuous at c, the limit as g of x as x approaches c is g of c, and now we just apply the last result where b is g of c, and so we get that we just get the result. So the limit of the composition is the limit of f of g of x, which is f of the limit of g of x from the last one. The limit of this, instead of calling it b, now we know that limit is actually g of c, and of course that's f of g, f composed g of c, and so we see that that limit is just that function evaluated at c, and so that makes it continuous. Maybe I should actually say that. Okay, so by the definition of continuity, we get that. And number 4 was really just number 3 again. It's just saying if you do this this says at every point C where this happens, where it's continuous at C. Well, if this is continuous everywhere it's defined, both of these are continuous everywhere defined, then the composition is going to be continuous everywhere the composition is defined. Now, I'm not going to prove the intermediate value theorem in this video. Usually you'll see this in a more advanced calculus textbook, something like might be called real analysis. But what I do want to do with this is kind of give you an idea of what's happening with this. And I think the best thing I can do is draw a picture. Okay? So, here we have a function. Okay? Here's our function f of x. Okay? And it's defined from some a to b, some closed interval there. And this is our f of x here, is this green function. And this is continuous. So intuitively we know what continuous means, right? We know it means you can draw the whole thing without picking up your pencil. And we want to make sure that this endpoint down here and this one up here have different y values. Okay? So we have different y values at f of a and f of b. Okay? And in fact, on this particular one, the interval a is -5 and b is 4. So it goes from -5 to 4. And we see that f of -5 is -22. And f of 4 is 50. So there's just a 0.450 here. Okay. And so we see those are different y values. Now we can pick any value that's between there, between the f of a and the f of b, that is between the -22 and the 50, and we could draw a horizontal line. That's our red line. Okay, so here's our n equals 2. Okay, and what this theorem says is that the graph has to cross that red line somewhere between a and b. So if it starts on one side of the line and it ends on the other side of the line, it has to cross between because it doesn't have any breaks in it. Now, if it was not continuous, there could be a break and it might skip over that line. Okay, but if it is, of course, if we weren't on both sides of the line, it wouldn't necessarily cross it. But if that line is somewhere in between, and so there's a value of c here, here, and here. There are 3 different values of c where this line crosses. The theorem doesn't say how many times it will cross. It'll say it crosses at least once. Might be more than once. In this case, 3 times. So there are 3 different values of c that are possible. That's what's going on with the intermediate value theorem. And intuitively, it should make a lot of sense. It should be pretty straightforward. If you're looking at it when you're thinking of this as this is something we can draw without picking our pencil up. In fact, you have to draw it without picking your pencil up. And you start on one side of the red line, you go to the other side of the red line, you've got to cross it somewhere in between. It just has to happen. Okay. Finally, one more property here. A function f is if a function f is 1 to 1 and continuous on an interval from a to b, then the first thing, either f is strictly increasing or strictly decreasing on the interval, and its inverse function, f inverse, is continuous on this interval f of a to f of b, depending on which order it goes. Okay, so let's do a proof of that one. So the first thing we're going to do is show that it has to be all increasing or all decreasing. Okay. Now we're going to prove this by contradiction. So how do you do a proof by contradiction? You set up your hypothesis. The function f is one-to-one and continuous on the interval a to b. And we're going to suppose it was neither increasing nor decreasing. Now if it's increasing, then if you put x1 to x2 to x3 in our interval a to b, and they're in that order, left to right, then if it's increasing, that f of x1 has to be less than f of x2, which is less than f of x3. And if it's all decreasing, that f of x1 has to be greater than f of x2, which has to be greater than f of x3. But if neither one of these happens, there has to be some combination of x1, x2, and x3 where f of x2 is not in the middle. If it were in the middle every time, then it's not all decreasing or all increasing. Okay? So there's one case. Either f of x3 is between f of x1 and f of x2, or case 2, f of x1 lies between f of x2 and f of x3. Okay, so if f of x3 is between f of x1 and f of x2, now remember f is continuous, so the intermediate value theorem says there's some c in that interval from x1 to x2 such that f of c equals f3, because remember f of x3, because f of x3 is between f of x1 and f of x2. This is like our red line again, is this y value. Well, wait a minute, that's going to be a contradiction, because this is supposed to be one-to-one. Every y can only come from one x as long as these x's are in this interval from a to b, and they all are. So that contradicts that, and so then our conclusion, our original assumption, was that it's neither increasing nor decreasing must be false. Okay, and in the same way it works here is if f of x1 is between here and here, that's the other possibility. And since neither one of these, both of these lead to a contradiction, then our original hypothesis, original assumption right here must be false. And the same kind of thing happens here. You do this with applying the intermediate value theorem. And so we see that it's got to be either f has to be strictly increasing or strictly decreasing. So let's look at the case where case A where f is strictly increasing. Now let's look at this. I'll read this, but we're going to look at the picture to make sense of this. The image of the interval AB under the function f is f of a to f of b. Since this is increasing, we know f of a is the smaller than f of b, and all the ones in between a and b will be between f of a and f of b because it's increasing function. So that's the interval there. So we're going to let y0 be any specific point in the interval from f of a to f of b. And we're going to let x sub 0 be any be the image of f inverse of y0. Okay? So what does this tell us? Now, first of all, I'm going to start with the idea that the x's are the inputs for the original function f. The outputs will be y. But inverse function works backwards, so we're going to think of its input as being y and the output of f inverse being an x. So think about it that way. Because remember, the f inverse goes backwards. It reverses the order pairs, reverses the function. So we can let x sub 0 be the f inverse of this specific y0 that we start with. So we're going to try to show that let's see, we want to show that we're continuous here. So we're going to start with a y value because we're going to try to show that the f inverse is continuous. Okay? So that's like our c. Right? In fact, maybe I'll say that c equals, just to make that a little bit more clear. Okay, now let's start our proof. We're going to try to do this with epsilons and deltas. So suppose we're given any epsilon greater than 0, and we want we just need to make sure that we're choosing stuff that's within our interval. Okay, and we want x minus epsilon, x of 0, to x of 0 plus epsilon to be a subset of our original interval AB. As long as we choose it that way, then we're okay. And if it's not, just make it narrow. Pick a smaller epsilon, because we want to think with the small epsilon to make this work. Now, since f is increasing, f maps this interval from x minus epsilon to x plus epsilon onto the interval f of x sub 0 minus epsilon to f of x sub 0 plus epsilon. Now let delta be the minimum of the distances y0 minus f of x sub 0 minus epsilon and f of x sub 0 plus epsilon minus y0. Now if y0 minus delta is less than y0 plus delta, then we get what we want here in terms of the function, and we show that it's continuous. Now, that probably was hard to follow. So let's take a look at a picture here and see if we can make more sense of this picture. Okay, so here, what do we have graphed? Okay, in blue we have the original graph f of x. So f of x, this is y equals f of x. So it's the standard order for the original function f. The inputs are f are the x values down here, the horizontal, and the vertical are the y values, the outputs over here. But remember, one way to look at the inverse function is to look at exactly the same graph, but now think of the y values as your inputs and the x values down here as your outputs. That's one way to think of the inverse function. So since we're switching the role of input and output, your deltas are going to be over here on the y part, and your epsilons are going to be down here on the x part, which is backwards from our normal way of doing it, because we're looking at the inverse, which is the backwards function. Okay? So now let's look at what we got. We start with our y0 here. Any y that's in over here. Then we pull it back by doing f inverse of that. We'll pull it back here, and that will give us a corresponding x sub 0, which is f inverse of y sub 0. So here's our x sub 0 are on this orange line, and our y0s on this horizontal line. So this is y equals y0 is the red line. The horizontal vertical orange line is x equals x sub 0, which is f inverse of y0. We started with the y0. Now what we want to do is we want to pick our epsilon now, and we want to go x sub 0 plus epsilon here and x sub 0 minus epsilon here. And this whole thing may be defined on some interval. Let's say our interval runs from, say, A to B. There's our original interval there. Okay, why is that disappearing on me? I don't know. I don't understand. Okay, there we go. One time. Okay, so we have that. Now, so long as this interval here, from x sub 0 minus epsilon to x sub 0 plus epsilon, as long as all these x values are still between a and b, we're good to go. All right, now, with that, then let's go back now and apply f here. If we apply, of course, we apply f to this, the f and the f inverse cancel. F of x sub 0 is back at y sub 0. That's where we want to be. Now let's look here at f applied to this. If we take f of x sub 0 minus epsilon, that goes up this vertical line and sees where it crosses the original graph, pulls that y across here. And this green line down here at the bottom is f of x sub 0 minus epsilon. Now do the same thing for the right end. If we do f of x sub 0 plus epsilon, it should be higher because this is an increasing function. We take that f value, that's up here, and that's where this black line is. And so that y value there is f of x sub 0 plus epsilon. Now let's look at the distances here. We've got one distance from the red line to this top line. That's delta 1. Okay? and then we look at this distance to the bottom line, let's call that delta 2. Now whichever one of those is the smallest, we want that to be delta. So in this particular case, I've got it drawn where the smaller one's on the bottom. So this is delta right here. So then this value down here at the bottom becomes y0 minus delta, which in this case the y0 minus delta is the f of x of 0 minus epsilon. But up here the y0 plus delta is a little below the f of x of 0 plus epsilon. So if we only pick pick any, now take any y value in here, could be anywhere between here and here, right? When we pull it back across here, notice that the x value is going to be in here. It's going to be inside the purple. Notice this time, since we're doing it backwards, we want the graph to run out the top or the bottom, not the left or right. Because any y we pick here, like even a y up here, is going to come across and it's going to come down here. None of them, whereas if it went out the side here, there might be something that, like we went way up here, we could pick one that would come out here and it would be outside this interval down here. This is our target interval here. But by choosing it where we did, we made sure it fits inside. That's how the proof is working there. And if it's strictly decreasing, then the graph is flipped over where it's coming down, but the basic setup's the same, so I'm not going to go through the steps on that one. Okay? So these results show how we can build up continuous functions from existing functions that are continuous. And in the next video, we'll look and use these results to prove that most of the elementary functions we studied in pre-calculus are actually continuous where they're defined, and many of them are just continuous functions, period. And we'll look at some of those videos and those examples in the next video.